Ladies and gentlemen, welcome to this flight-2025 destination to New York. We are pleased to welcome you to this session and expect that you will have a safe and pleasant flight.
Fred, sorry to interrupt you, but passengers are complaining. The screens are not working. We are not able to display the safety video, so we can take off. Sorry.
Okay. So we stop now the comedy. And why we created this solution, so-called FlytEDGE, is to avoid those situations happening in reality, and they do happen, unfortunately. So we will be presenting you how edge computing have been helping us in our business for our customers, the airlines, in order to modernize, transform, understand the passenger experience. And that's what we're going to present. The solution is called FlytEDGE. I will just first talk about our customers. So we are Thales, Nico and myself. We are based in France, as you can hear. We have customers all over the world, and that's extremely important. And our customers have aircraft flying every single minute. At the time we speak, we probably have thousands of aircrafts flying. You can understand how important it is to observe, understand, monitor what is flying, and not only for the traffic control, but also from a passenger experience point of view. We deliver in-flight experience. So the seats have a small screen that you all know, but on the back end of the screen, there are plenty of things. There is a server. There are several network switches, several controls, and I will go through it slightly later. There is an absolute need to monitor what is happening. And in Thales, we have sites a bit everywhere in the world. Our headquarters are in Florida and in California. And we have then sites, or let's say sales reps near our customers, wherever they are, we tend to be. And that's the way we are. One number, and that will be the last number about Thales IFE, in-flight experience. We have close to 2 million passengers flying every day that are using our systems. So it's an intensive use. And when it fails, it can be a serious problem. And some of you are from the airlines. I know some of you, naturally. Indeed, that's something that is extremely important to know how it works and how it performs. Now, what is a traditional in-flight entertainment or experience system? So let me just put a bit of context here. Most of the aircraft you are flying today, when people want to upload a new movie, they go with a hard drive in each and every aircraft, plug the hard drive, transfer the data, wait. 30 days after, they go again, update, wait. So those cycles are super slow and surprising. When you join the industry, you're surprised about those processes. This being said, those processes exist, and they are meant to be transformed, and that's what we work on. Naturally, you may foresee or you may expect that an IT approach over-the-air content, software development, monitoring, observability that we will be talking about makes much more sense, and that's what we've been transforming. There is one aspect that still needs to be understood, and that may explain why people with their sneakers plugging sometimes is important, is that connectivity is extremely limited in an aircraft. You guys have probably flown through an aircraft that has connectivity, and you had internet on board. Internet is for the passengers first. It's not for people operating the system. That's an important point. But it is extremely costly when it is flying. The cost of a gigabyte using satellites is 5 to 10 times more than the cost of a gigabyte over cellular. So we have to be, it is a precious thing that we have to be careful with. Latency. Traditionally, when you go with geo satellites, you can expect 600 to 800 milliseconds latency. So that's quite of a challenge. That's a shared pipe. First, customers are the passengers, and then people delivering systems can ride on, but the less, the better. When it commutes from a beam to a beam, a bit like when we roam with our cell phones, sometimes you can lose few seconds. That's what it is, and that's somehow the nature of this. And last point, because it's aviation, because it is a safety critical, every process is predefined, extremely controlled. Most of you that are here know how important it is to have a safe flight, and that's what is pushed. And naturally, there is nothing we would do without being approved by the authorities, be it the FAA here in the US or the ESA in Europe. And those processes are important to comply with. Now, still, we know that the experience is transforming. And most of the time, we compare our seatbacks when we are flying, or our experience when we are flying, with the one we have at home. We kind of see a gap. We kind of compare on this one. But we see many airlines now pushing to have much more instant, let's say, fresh experience. It has to be deployed remotely, very clear. It has to be deployed quickly. If I want to deploy for Christmas, I don't want to deploy 30 days before. I would like to deploy probably a few days before. We see in the aircraft coming more and more devices. The seatback that is on, well, the display that is on the seatback, this one we know it, but most of the people now are using their personal devices, and they may want to access to the same experience, the same content, same capabilities. And last but not least, because it has to be personalized, because most of the experience that we live in our homes is personalized, there is a tendency to, let's say, bring an experience that is very linked to what you are or what you consume or what you are used to. In order to do so, there is no way it can happen without getting data from the passengers, from the world, let's say, of the consumers, and that's where observability kicks in. With a need to transform the experience, there is an absolute need to collect data, process it, observe, and it can be data about the passengers. I mean, I've been referring to it, but it should be also data about the system, the performance of the system, data about the usage of the movies, especially for the licensing, is extremely key. So all this to say, observability is key, and that's what we've been working on. I'll go quickly into the transformation that we have been pushing through. Still a connected aircraft. We created a big infrastructure on the ground that is really, let's say, limitless compute, limitless storage, limitless capabilities, with connections possible to any cloud, including on-prem infrastructures whenever the airlines have on-prem infrastructures. And we brought on board an edge computing piece. So we call it an onboard data center. Sometimes it may look a bit arrogant. Nico will describe it. Still, it has a lot of capabilities. We work to bring at the edge, so in the aircraft, an IT piece that extends what happens on the ground or what is on the ground. And that's the way we've been building or creating end-to-end cases. Still, this has to work disconnected. Still, this has to consume as less satellite communication as possible, because that's still precious. But definitively, it allowed us to move into a capability where each and every aircraft becomes kind of an IT flying piece, where we have a need to monitor the way we would monitor in data centers, and I've been operating a few in my past. We need also to bring openness on what we deliver. You see the logos on the bottom right. Bringing actors of the consumer world requires to have on board a capability that is very close to what you would see in data centers. And that's the way we've been working on, and it allowed us naturally to modernize the experience. Back to reality. In an aircraft, an ODC is this thing. It is installed in a specific part of the aircraft, usually the avionics bay, that has almost no cooling. It has to be able to sustain I will be in Celsius, plus 85 degrees Celsius when you are on the tarmac in Doha, and it's 50 plus outside. When they turn on, it has to turn on. The thing that we pushed in this architecture was really to bring on board a piece that was strong enough, capable enough in order to enhance, upgrade, modernize the passenger experience. And we put on board an hardware that is software-centric or software-defined. It is a software that is distributed. It's an hardware that is extremely resilient to failures. But that's not the only one that we are monitoring. If you look at what an IFE is, you have a head end, you have seats. In the head end, you have several elements, be it storage, be it network. In the seats, you have naturally the screens, very simple, but you also have cables and switches to distribute data over the cabin, and you even have power. So here, really, to charge your phones, power that is distributed within the cabin. And that's what we've been working on. When you look at the number of devices that is in an aircraft, it becomes almost an IT, IoT piece that is flying, and that's where we've been working with Datadog in order to bring new capabilities. And now, Nico, I give you the testing.
Thank you, Fred. Now I'm going to walk you through the journey of implementing observability on board an aircraft with FlytEDGE. And this journey started with a simple statement, which is that we didn't just want to monitor aircraft. We wanted a unified platform, a single pane of glass that would allow us to monitor all the critical layers, all the stack that we deploy both on board and on the ground to have a full understanding of our system. So what we did was to monitor from the cloud application up to the passenger experience. We needed everything. And so the first step for that was to choose a monitoring platform. So there is no surprise about that. We are using Datadog, of course. Datadog, before this project, was already a great partner for Thales, mainly for payment business. So it was quite natural for the cloud part of the observability to go to Datadog. However, going to a cloud-based monitoring to monitoring devices that are sometimes disconnected, that are quite limited in resources, there is some gaps. And to fill those gaps, we've done many POCs. And Datadog has been a great partner for those POCs. They have helped us to validate all the hypotheses we took. And they even helped us to push the boundaries of what Datadog was able to do at that time. Now there is some features that you know as historic metric that allows to ingest metrics way back in the past, to backfill metric in the past. This didn't exist at that time, and it was a big limitation for us because, for instance, aircraft can be disconnected for several hours, several days maybe, and being able to backfill the data when we are able to retrieve everything was a big need for us, and Datadog helped us to push this limit. Now, going back to the ODC, the onboard data center, I will just give you some feedback, some cool facts about this box because we are really proud of it. What is it? So we have 6 computing blades that both bring computing power, but also storage. We have fully redundant power supply and fully redundant networking, meaning that we can afford losing quite few pieces of this box before it actually fails. In practice, it contains 48 Intel cores. It can go up to 96 terabytes of storage. And to get everything to work together, we are using Kubernetes to orchestrate all the workloads. And we are using Ceph that allows us to bring all the storage together over network and expose it as either block storage or S3 buckets. With that, we basically have an embeddable cloud platform that we can put in an aircraft. And what is quite amazing to me, at least, because we have hardware engineers that build this box, all of that must run on less than 300 watts, which is basically the minimum consumption for a hairdryer. So it gives you a scale of the achievement. And basically, this is the box that we want to monitor. We want to add observability to this box to allow monitoring everything that happens in the aircraft. So we have some specific requirements because we are in an aircraft. We have limited connectivity. We have some specific regulatory needs. And these requirements are the following. First of all, we want to collect all the metrics and logs that are produced in the aircraft. That's the basics of observability. However, connectivity is not cheap, as Fred mentioned. So we want to make sure that we make the best use of it. And for that, we need to filter, to transform, to compress, to do everything we can to fit only relevant data into our connectivity pipe. Also, we want to be fully resilient to connectivity loss. If the aircraft is disconnected for several hours, several days, we don't want to lose any data. We want to retrieve everything as soon as the aircraft is connected again. We also want to prioritize data based on connectivity. Let's say that I have really critical data, let's say cybersecurity related events that I want to offload. We want to be able to offload this data as soon as possible, even if we are on SATCOM connectivity. But we also want to be able to wait for the aircraft to ground to send less priority data. So that's something we want to achieve. And finally, we send everything to Datadog, of course. But we also want to do data science, to do BI. And for that, we need the capacity to send this data to multiple destinations. And we don't want the aircraft to send the data multiple times. So we need a solution for that. So this is a really schematic view of what is an ADC. It's a Kubernetes cluster, 6 nodes, microservice running on it. How many people in the room are operating or using Kubernetes? Okay, so I won't teach you anything. You know the best way to monitor a Kubernetes cluster with Datadog is to deploy the Datadog agent on it. And that's what we did at the very beginning. It's quite simple, Datadog agent on every node. Everything is collected naturally, and the data will be sent to the ground as soon as we have connectivity, be it SATCOM, cellular, or airport Wi-Fi. It works great. It works great because it's what it's meant for. So we can collect metrics, logs. Everything is back to Datadog. We are able to monitor, create dashboard. That's amazing. We have some capacity to filter and transform the data. We can filter sensitive data, but it's limited compared to our use case. On board, we want to do aggregation, complex filtering, and that the agent is not capable of it. It's somewhat resilient to connectivity loss, but it's actually not really documented, and we don't have an actual control of the duration we can tolerate. So it's not really there. We are not able at all to prioritize some kind of data depending on connectivity, of course, because it's a really specific use case. And again, we can send the data to multiple Datadog instances, but that's it. So it doesn't match really our situation. So back to the drawing board. It was back in 2021. At that time, Datadog has acquired a project called Vector, which is a small piece of software implemented in Rust. It allows to take data from many sources, to transform this data, mainly using a specific language called VRL, Vector Remap Language. We can do quite complex operation with Vector, and to offload everything to a large amount of things. It can be Datadog, but it can be any kind of destination. So we decided to replicate the agent-based architecture with Vector instead of the Datadog agent. So it looks quite the same, and it will communicate the same way the Datadog agents did. So again, we kept the same qualities as the previous try we did. But now we have really a full control on how we can filter and transform the data. We can actually enrich the data on the fly. We can correlate. We can aggregate. It's quite powerful. However, for the next requirement, it's still not there yet. It is somewhat also resilient to connectivity loss because there is a back pressure mechanism that allows to stop collecting data if we are not able to send it downstream, but that's about it. In order to tackle this issue, we added another instance of Vector on board. This instance, the sole purpose of this instance is to buffer the data as long as the connectivity is not available. And this buffer, and that's why talking about Ceph earlier is important, this buffer is stored on the Ceph storage, meaning that this storage is replicated across the cluster, meaning that if the aircraft is disconnected and we lose the blade on which the aggregator is running, yet we don't lose any data because the bufferized events are replicated everywhere. This way, we are able to tackle the resiliency to connectivity loss. And actually, just by scaling the size of the buffer, we are able to know how long we can afford to be disconnected without losing any data. Still 2 points to cover. So what we did after is that we needed to implement some ground infrastructure to get a better control of how we communicate with the ground. Communicating directly with Datadog didn't allow us to fine-tune the protocol being used, and we talked about 700 millisecond latency. When you have this kind of latency, you need to be carefully configuring the protocol you use to communicate. And so we decided to implement an Azure Event Hub to collect all the logs in our infrastructure. Downstream this Event Hub, we have another instance, again, of Vector. But this time, the role of this instance is quite simple. The role is to route the data everywhere we want. So some examples that we use internally is that on one side, we can route the data to Datadog. But we also route the data to our data platform so that we can do data science, machine learning, and so on. Another use case is that we have some customers that may be interested to also retrieve their data on their own Datadog instance. And this is something that we can do seamlessly with this architecture. Last point on that, we are also able to generate on-the-fly custom metrics that allows us to better understand which aircraft is sending which kind of data, which services on board are consuming the most bandwidth. We can directly generate those metrics in this new Vector instance. So with that, we have the multipath routing. I kept the connectivity-based flow control as the last item, because this is the last one we tackled, actually. So the question is here, we have a flow of data, and we want to make sure that we can control which data is sent when, based on what connectivity is available. I have high priority logs. I want to send them whatever the connectivity is. Low priority log, I will send them when the aircraft is grounded. For that, we added another component that we developed ourselves. that we put between the aggregator and the actual ground connection. The role of this component will be basically to open or cut the valve for the flow of data, depending on connectivity. If we look into detail, actually the architecture is quite simple. We modified the aggregator to be able to route the data to multiple outputs based on some criteria. It can be, is it a security log? Is it a metric? What kind of log is that? We are able to route based on any custom-defined policy. After that, we have our controller that is basically able to cut or open the flow for all those routes. And having separate buffers for each priorities allows us to keep each priority class stored as long as necessary, depending on the policy. And with that, we achieved the last point, which is connectivity-based flow control. And you know, observability is never enough. So actually, we haven't stopped there. We have passengers that are using those microservices, that are using the UI we expose on board to enjoy movies, to enjoy a 3D map of their flight, to listen to music. And we wanted to have a better understanding of how they use the system, which part is working the best. And so we wanted to add observability for that, up to the passenger experience, as I said at the beginning. And for that, we have deployed Datadog RUM directly in the passenger UI. It will basically collect usage, the passenger usage. To get the same properties that we wanted, being able to store the data temporarily when connectivity is not available, we implemented a dedicated proxy for RUM that basically works pretty much the same as the offload controller. And for that, we finally have full observability on board an aircraft. So let's look how it looks like in real life. So what we like to do first when we observe an aircraft is to know where the aircraft is in its flight, what connectivity is available, what's going on. Knowing if an aircraft is flying or not is really important for us because there are some operations we are not able to do in flight or even not allowed to do in flight. Deploying new version of software, doing a remote reset of the infrastructure, we have to wait for the aircraft to be landed. So we are able to generate many custom metrics that are relevant, that are just really specific to the actual aircraft. After that, we have all the usual metrics, usual system metrics, CPU, RAM, per process, per containers. We are able to understand how the storage is behaving, which service is using most storage, how the storage is consumed by the services. Up to the passenger experience, where we can know what application is the most used per passenger. For instance, here we can see that the second most used URL is the PAX journey, which is where we host the 3D map. And we know that actually the 3D map is something that passengers really enjoy during their flight. So it's not quite surprising. We can know which content passengers prefer, and based on that, do some optimization, some recommendation, and understand better how passengers interact with the system. Last but not least, Thales is known for cybersecurity, and it's quite a concern for us. We have many cybersecurity-related monitoring solution deployed on board, and this is one of them. We have an onboard web application firewall that is able to block any suspicious request, and on this dashboard we can see all the suspicious activity we detected. Be reassured, this is a dev environment, this is not an actual aircraft. So we have learned a lot of things on the technical standpoint. But observability is not only technical. Some other stuff we learn in this process is that first, observability is really for everyone. When you look at dashboard, when you look at SLOs, at monitors, it can feel that it's something that is only for DevOps engineers. Actually, getting everyone on board, from the developer up to the CEO, is the best way to go. It creates a common language between everyone in the organization and allows to share topics that otherwise would be hard to explain to each other. Also, the more users you have for your observability, the best the data will be, because people will bring new requirements for other teams, and it creates good dynamic between teams. The other thing we learn is that standardizing logs, but also standardizing tagging, metrics naming, is really a major topic if you want to, again, break silos between teams and create a common language. Finally, and this point is more specific to the edge or IoT architecture, we need to observe our observability pipeline. There is too many ways to bring bottlenecks by creating more data that we can afford, or using the system too much, not optimizing the data we offload. We need to monitor the way we collect data from the aircraft to make sure that we don't reach any of those bottlenecks and to keep the system healthy. And actually, this is something that must be done early in the process because it's quite hard to implement afterward. So Fred, let's you back to the
last click of the appui. Well, that's okay. So few aspects that have been treated here. So first of all, modernizing aviation is possible when we look at it from an IT angle, and that's really what we've been doing, looking at it with the same view you look at data centers, or you look at software-centric solutions, or you look at let's say, modern capabilities that are today software as a services, such as Datadog, helped us to modernize aviation, our products especially, and then being able to bring it to our customers. That's an important aspect that we looked at and we considered from the early stages of our product. Second one, partners like Datadog. Initially, when we looked at them, we considered it would not be possible to go at the edge. They acquired Vector. Nico covered it. Getting close to those partners helped us also to leverage on their innovation, their capability to invest, their capability also to develop the product, and we saw it in the conference this morning, hundreds of products coming through. Customers have to be with us, and there are some in the room, and thanks for being here. Customers have to be with us. Indeed, using data is not only the problem of Thales delivering an IFE, it's also how our customers want to leverage on those data to change their processes. And last but not least, and I'm happy because those slides were made naturally before the conference, software is king in our world. Even in aviation, where people from time to time believe that hardware is somehow the king, hardware is a differentiator, but definitively software remains the most important thing that we bring. Being able to deploy, rollback sometimes, being able to update regularly, being able to bring a software stack that allows new use cases to come is just a must, and that's what we've been looking and working towards, and that's my last takeaway.
Thank you both very much. If anyone has questions, please come up to the microphone right here. We've got time for some follow-ups with Fred and Nico. I'm curious, what happens when there's an incident?
Well, we tackle it first. We open a ticket also. And that's what we do when we have incidents. So There are different conditions depending on the emergency of the change. When an aircraft is flying, don't touch. That's the rule, that's the processes, don't touch. But you can prepare the action when the aircraft grounds, then we are able to trigger the change. That's one. The second one is we've been working a lot to have self-healing processes. So thanks to the edge computing capability that we have, we put in place several self-healing, and it's not only a soft reset. I mean, it's much more educated than this. That's the way we've been learning. And then learning from the failures, enhancing our software, making sure that it works in different conditions. That's what we've been doing. There was a question here.
So, with the agents you're deploying to your onboard cluster, are those standard agents per server, or are they like a special IoT agent? Do basically every plane have 4 or 5 hosts, Datadog hosts associated with it? How does that kind of fall out?
So the final solution, as I mentioned, is using Vector as an agent, which is a standard open source version we are using. Nothing specific, actually, except the configuration that we did, but that is not that complex, actually.
There's a question. There are 2 questions. Yep.
Okay. 2 questions. One.
Use the mic.
Oh, sorry. Wow, I have a mic. Okay. One, does the size of the onboard data center, does that vary based on plane size? Like, obviously, with an A380, you want something a little bit bigger than like a regional aircraft. And then 2, did you guys consider protocol buffers to reduce data size when transmitting over the satellites?
I take 1, you take 2. So, indeed, in the aviation, you have different sizes. The approach we took was to have one size for all the platforms. For a few reasons. Sometimes it's a bit oversized, especially in terms of capabilities. Storage may not be completely used, but we wanted to have a resilient data center no matter the platform. So we still use this size. It's like this in reality. It's one single size. We just have a different configuration. One of the blades is slightly different depending on the aircraft we address. But size, weight, and somehow power consumption is similar no matter the platform. And even on an A3, I should take a 350 rather than A380 because we are not installed on A380. But even on A350, which is a really wide body, only one data center is enough to serve the 300, 400 passengers streaming content from their display to the Odyssey. And regarding using protobuf, so it's one of the hypotheses we still have to, if we want to keep optimizing the data usage. And actually, there may be an even best solution. Since we have Vector at the input and at the output of the connectivity, we could use directly the Vector codec, which basically relies on the internal memory mapping of Vector, which is the most efficient way to transfer data between 2 Vector instances. Yeah, we are looking at more solutions to optimize, and even compression is one of them. So yeah. There was one more question.
Hey guys, I just had a question around out of order. So with being so disconnected for a long period of time, do you ever have to struggle with or deal with messages arriving out of order when they get to the ground side control?
Yeah. Actually, sometimes they do. Luckily enough, Datadog allows to reorder data when you inject anything, actually. So it's not quite an issue, at least for the Datadog part. For the data science part, it's a whole new problem because indeed receiving data out of order is a mess and we have reordering. But anyway, everything is time-stamped at generation time, so we are always able to reorder data afterward.
Thanks.
We've got time for just one more.
There are two.
They're going to have to fight.
Oh, no. Max.
Two questions. Take one if you have to. One, how do you know if the plane is on the ground or in the air? Do they have an API, and is it the same for all planes? Two, with Starlink coming, what are you planning to do for that, and what will that allow you to do?
You cheater. I said one.
So yeah, we tend to have one unique solution no matter what. So Starlink, but there are other actors now that are really modernizing. Indeed, the LEO satellite brings a lower latency, and we are looking at 100 milliseconds, in the range of, let's say, 100 milliseconds. So we do integrate with any connectivity partner that comes, with any technology that they use for their satellites. The good thing with the Starlinks of the world, and there are few that are very good in the industry, is that they are bringing us more bandwidth. Still, we just take a bit more, because ultimately, the bandwidth will be consumed by the passengers. You'll bring new use cases. You'll bring probably live TV to the next level. So ultimately, even with the Starlinks of the world, we tend to apply the same approach and reduce our consumption as much as we can. That was the last one. I don't know if you take it or not, Max.
Thank you for the landing. I appreciate you getting us back home to our city of choice very safely. Please give Nico and Fred a big round of applause.